Hello students. Hello and welcome to this video. In this video, we will solve question number 191 to 200 of binomial theorems. The link to download the PDF will be in description. At the end, I will show you how you can maintain an updated copy of the PDF. Also, at the end, I will show you my website where you can come and ask questions because YouTube comment is not really suitable for solving problems. So without further ado, let's get started. Question 191 says that show that C0 plus C1 times C1 plus C2 times C2 plus C3 times and so on up to Cn minus 1 plus Cn is equal to n plus 1 to the power n upon n factorial times C1 C2 up to Cn. So we take the Rx factor of the given product Tr is equal to Cr minus 1 plus Cr, which we can write as n plus 1 Cr, which is equal to n plus 1 upon R Cr minus 1. Here Cr means NCR and here it means NCR minus 1. It was n plus 1, so written explicitly. Now once we have that, we can write the given series or product as n plus 1 upon 1. This should be C0, yeah, and n plus 1 upon 2, C1, n plus 1 upon 3, C2, and so on up to n plus 1 upon n, Cn minus 1. So we have got n plus 1 to the power n by multiplying all the n plus 1, and 1 times 2 times 3 of the denominator becomes n factorial times C1, C2 up to Cn. C0 is basically 1. Question 192 says that if n is a positive integer, prove that 1 upon 1 factorial times n minus 1 factorial plus 1 upon 3 factorial times n minus 1 factorial. This should be 3, n minus 3. And then 1 upon 5 factorial times n minus 5 factorial and so on up to 1 plus n minus 1 factorial times 1 factorial is equal to 2 to the power n minus 1 upon n factorial. So what we do is we take out n factorial common, 1 upon n factorial common, and multiply each term by n factorial. So it becomes 1 upon n factorial C1 plus C3 plus C5 up to Cn minus 1, which we know as 2 to the power n minus 1, and denominator is n factorial. Question 193 says that prove that sigma r is equal to 0 to n minus 1 to the power r, and Cr upon r plus 3 Cr is equal to 3 factorial upon 2 times n plus 3. So we are given this relationship. We expand the given fraction. It becomes n factorial upon r factorial times n minus r factorial times r factorial times 3 factorial upon r plus 3 factorial. So you see r factorial gets cancelled, and what 3 factorial we take out, we are left with n factorial upon n minus 1 factorial times r plus 3 factorial. So what we do is we multiply and divide by n plus 1 times n plus 2 times n plus 3. So numerator becomes n plus 3 factorial, denominator becomes r plus 3 factorial times n minus 1 n minus r factorial. This is nothing but n plus 3 Cr plus 3. And then we substitute r is equal to 1, 2, 3 and so on. We get n plus 3 C3 minus n plus 3 C4 plus n plus 3 C5 and so on up to minus 1 to the power n plus 3 Cr plus 3. And then we add and subtract n plus 3 C0, that is 1. And we have n plus 3 C1, n plus 3 C2. And then we have that relationship, that is n plus 3 C3 and so on. That is equal to minus 1 to the power n plus 3. That's what we know, that is 0. So the expression which we have to compute, that is this expression, is equal to this, is equal to n plus 3 C0 minus n plus 3 C1 plus n plus 3 C2. So we evaluate that and we substitute and multiply. We end up with 3 factorial upon 2 times n plus 3. Question 194 says that if 1 plus x to the power n is equal to C0 plus C1 x plus C2 x square up to Cn xn, show that for n greater than or equal to 2, C0 minus C1 plus C2 minus and so on up to minus 1 to the power m minus 1, Cn minus 1 is equal to minus 1 to the power m minus 1, n minus 1 times n minus 2 times up to n minus n plus 1 upon n minus 1. So nc0 is equal to n minus 1 C0 minus nc1 is equal to minus n minus 1 C0 minus n minus 1 C1. nc2 is equal to n minus 1 C1 plus n minus 1 C2 and so on we have minus 1 to the power m minus 1 and cm minus 1 is equal to minus 1 to the power m minus 1 and minus 1 cm minus 2 plus minus 1 to the power m minus 1 and minus 1 cm minus 1. So we split everything into two factors and we have that C0 minus C1 plus C2 up to minus 1 to the power m minus 1 Cm minus 1. It becomes minus 1 to the power m minus 1 n minus 1 Cm minus 1, which is essentially n minus 1 factorial upon m minus 1 factorial times n minus n factorial, which is equal to n minus 1 times n minus 2 times up to n minus n plus 1 upon m minus 1 factorial. Question 195 says find the GCD of 2n C1, 2n C3, 2n C5 up to 2n C2n minus 1. So we know that the sum of these terms is equal to 2 to the power 2n minus 1. Thus, because D is a common divisor, so that we can have a form of 2 to the power k because it has to divide 2 to the power 2n minus 1. Thus, k will be between 0 and 2n minus 1. Let n is equal to 2m into r, where r is an odd positive integer. So 2n is equal to 2 to the power m plus 1 times r, and 2n c1 is equal to 2n is equal to 2 to the power m plus 1 into r. Thus, common divisor is less than or equal to 2 to the power m plus 1. We claim that 2 to the power m plus 1 divides all of 2n c1, 2n c3 up to 2n c2n minus 1. For odd positive integer p, 2n cp is equal to 2n upon p, c2n minus 1, pn minus 1. That is 2 to the power m plus 1 r upon p, c2n minus 1, pr minus 1. That is equal to 2 to the power m plus 1 into r times 2n minus 1 cp minus 1 upon p. Now 196 says that show that sigma r is equal to 0 to n ncr into sin rx into cos n minus rx is equal to 2 to the power n minus 1 sin nx. So we can write this as nc0 sin 0 cos nx plus ncn sin nx cos 0x plus nc1 sin x cos n minus 1x ncn minus 1 sin n minus 1x cos x, and so on up to ncn sin nx cos 0x plus nc0 sin 0 cos nx, which is equal to c0 plus c1 plus c2 up to cn sin nx is equal to 2 to the power n sin nx, and therefore sigma ncr sin rx cos n minus rx is equal to 2 to the power n minus 1 sin nx. Question 197 says that a times c0 plus a minus b times c1 plus a minus 2b times c2 up to a minus nb sin times cn is equal to 2 to the power n minus 1 to a plus minus nb. So we can write this as a times c0 plus c1 plus c2 up to cn minus b times c1 plus c2 2c2 plus 3c3 up to ncn, which is equal to a times 2 to the power n, which we have evaluated earlier, and nb 2 to the power n minus 1, which is equal to 2 to the power n minus 1 to a minus nb. We have evaluated this one earlier to be n times 2 to the power n minus 1. Question 198 says that a square times c0 minus a minus 1 times squared times c1 plus a minus 2 squared times c2 up to minus 1 to the power n a minus n whole square cn is equal to 0 if n is greater than or equal to 3. So we are given this. So we can write this as a square c0 minus c1 plus c2 up to minus 1 to the power n cn, and 2a times c1 minus 2c2 plus 3c3 up to minus 1 to the power n cn, and c1 minus 2 square c2 plus 3 square c3 minus so on. All these series have been proven equal to 0 earlier, and thus sum is 0. So you need to refer to earlier solutions, and then you will find that this is 0. Question 199 says that if A0, A1, A2 up to An are B in an AP, prove that A0 minus A1 C1 plus A2 C2 up to minus 1 to the power n An Cn is equal to 0. So we write that A0 is equal to A1 is equal to A0 dot D, where D is the common difference. A2 is equal to A0 dot 2D, and An is equal to A0 plus ND. Now we have this given expression. We write this as A0 plus A0 minus A0 plus D times C1 plus A0 plus 2D times C2 and so on up to minus 1 to the power n A0 plus ND Cn. So this becomes A0 times C0 minus C1 plus C2 and up to minus 1 to the power n Cn and minus D C1 minus 2 C2 and so on up to minus 1 to the power n Cn. We have proven the two series in question equal to 0 earlier, and thus we have this sum is equal to 0. Question 200 says that show that for n greater than 3, sigma r is equal to 0, minus 1 to the power r, a minus r, b minus r into c minus r is equal to 0. So given expression becomes ab minus a plus b times r plus r squared times cr. So this will lead to three different series, C0 minus C1 plus C2 up to minus 1 to the power n Cn, and A plus B times R will lead to C1 minus 2 C2 plus 3 C3 and so on up to minus 1 to the power n Cn. And the third series will be C1 minus 2 square C2 plus 3 square C3 up to minus 1 to the power n square Cn. And we have proven these three series in the question equal to 0, so that the sum is 0. With this, we come to the end of this series. So now I'll show you my website from where you can download the PDF of all three books. So we have Algebra as second link, third is trigonometry, fourth is coordinate geometry. Coordinate geometry is not complete yet. I'm working on conic sections right now. So when you download, you notice the date and you add that to your PDF because the PDF will not contain the date. After 15 or 30 days, you come back and see if a new release has been done. So once you see that a new release has been done, you download and update the date of your book. Okay, I cannot put the date in PDF because it will make existing links invalid. Also, coordinate geometry is there with HTML format as well. So if you want, you can read online as well. For asking questions, you can click the 8th link or directly come to kunjika.astavak.org and you can ask questions here after making a login. I don't know why it is slow. So the tags, if you see, are algebra, calculus, coordinate geometry, geometry, probability, trigonometry, and the general tag mathematics is there. So you can use these tags to ask questions. So make a login here and ask questions if you have questions to ask, or use it to answer your questions. I'm trying to build a community here which can help each other. So with this, I will end this video here and we will meet tomorrow again with 10 more problems of binomial theorems. So thanks a lot for watching the video and I'll see you tomorrow in the next one. Till then, have a great day ahead. Stay curious, keep learning, and most importantly, enjoy.